Well, for those of you watching the video, welcome to class. I mean, not that anyone's on Zoom right now, but if you're watching the video later, we finally got the internet to work apparently. So great. You always have to find out the first couple, three terms just so I know which thing's going to cancel. Like it just never clear to me until I write it down. And then the last couple things, so like 1 over, I'm going to plug in n equal to 499 and get 1 over 499 minus 1 over 500, and then plug in 500 to get 1 over 500 minus 1 over 501. So let's see here. The -1/4 and 1/4 cancel. The -1/5 and 1/5 cancel. The -1/6 would cancel with the 1/6 that came after it, all the way till. So here you can kind of see what's happening here. So over here, this thing would cancel with what came before. This thing cancels with what comes after. And so we're left with exactly 1/3 minus 1 over 501. And yeah, you could make that one fraction, but again, we don't particularly care. So again, these are examples of telescoping sums. They do come up occasionally. And actually they come up, at least in my opinion, if you're proving this formula in question 9 on your discussion sheet, it typically requires the use of a telescoping sum to kind of make that work. There might be another way of doing it, but the way I know how to do it is to use telescoping sum. All right. I think that's a pretty good brief overview of sigma notation. Again, you're really just thinking about taking, so I made a small mistake here. It's not a huge deal, but I made a small error, which people make all the time, which is writing the wrong subscript here for the letters I've used here. I should have really written from n equals 3 to 500, not from I equals 3 to 500. The subscript here, or the index here, should match the letters you were using here. All right. Let us move on and talk about anti-differentiation. So sorry, yes. So antiderivatives. Really, the name says it all. You're undoing what a derivative would do. Or inversely, if you find the antiderivative, the derivative should undo that and get you back where you started. So what I would say should be kind of your overarching idea here for antiderivatives is that if you take an antiderivative of a function and then take the derivative of that, you should end up back where you started with the same function. Or vice versa. If you take a derivative and then an antiderivative, you should end up back at the same function you started with. That's the whole story about antiderivatives. Now, there's a lot more work in finding some types of antiderivatives. Like there's some antiderivatives that are much more difficult to find because you have to use special methods. But at the end of the day, the whole idea is that the derivative of a function and the antiderivative of a function undo each other and you get back to the same place. So for example, so unfortunately, at this stage in the game, we don't have the nice notation for antiderivatives that we're going to use eventually. So we're kind of stuck with this unwieldy, like using capital letters for antiderivatives and lowercase letters for regular functions. That's pretty typical. So usually we would write that either capital F of X is an antiderivative of little f of X if, not surprisingly, the derivative of capital F is equal to little f. Again, exactly displaying or exhibiting that undoing I just mentioned. Or you could alternatively write that capital or lowercase f of X is an antiderivative. Can I spell the words? Yes. Of f prime of X. People kind of use either one, depending on how they're feeling. So for example, I could say f prime of x is equal to 2x plus 3 plus cosine of x. And then ask you all to find the original function, the antiderivative of the derivative. Okay, well, I'm just trying to find a function whose derivative would be 2x plus 3 plus cosine. So what's a function whose derivative is 2x? Right, classic. What's something whose derivative is 3? And which trig function has a derivative equal to positive cosine? Positive sine. Right, the derivative of sine is cosine. So the antiderivative of cosine is sine. And then if we want to be general, and we typically want to be general, we slap on a plus c. Because what's the derivative of a constant? 0. So you could add any constant here, 7, pi, e, 1,000, a billion, whatever, and the derivative would still be 2x plus 3 plus cosine of x. So usually when you're finding an antiderivative, you end it with a plus c to make sure that you've covered all possible cases. Or we could do something like, so I should be looking at my notes. Yeah. If your function f of x is, let's say, x cubed plus the square root of x plus 1 over x to the 5th, we want to find capital F of x, which, sorry, just say, hey, Jay, scooch it up. Again, if you read this, you should understand this notation to mean they're asking you to find the antiderivative. Right? That is what is heavily implied by this, even if they don't actually write out those words. Eventually, we'll just say, find the antiderivative of f of x. Like that. That's the notation we'll eventually use, but we haven't really talked about like why we use that, so we probably shouldn't do that. Because there are reasons why we use this notation. Oh, we did? Okay, so we can totally also just start using that notation if we want to. It's pretty, I mean, it's used everywhere. So you can find capital F of x, or you can write it as the antiderivative of x cubed plus, let's change this to powers of x. So we're going to have x to the 1/2 plus x to the -5th. And you do need to end your antiderivative notation here with a dx, which is called the differential. And it's really just telling you what variable you're anti-differentiating with respect to. What I would say for now, when you see these two symbols paired together, and they're always paired together, these two symbols are just instructions telling us to anti-differentiate. Just like ddx of x to the 5th is an instruction telling you to differentiate. Same idea. So for this antiderivative, we're going to use what I typically refer to as the anti-power rule. So for derivatives, like the derivative of x to the 5th, the coefficient is the power and the power reduces by 1. To find the antiderivative, this doesn't always work, but it works here. You're essentially going to do the opposite things in the opposite order. So instead of first multiplying by the exponent and then subtracting 1 from the exponent, we're going to reverse those in the opposite order. So we're first going to add 1 to the exponent, and then we're going to divide by that exponent. So the antiderivative of x to the 3rd is going to be x to the 4th divided by 4. Or if you prefer, you put the 1/4 out in front. I don't really care either way. Same deal here. You're going to have x to the 1/2 plus 1 is 3/2 divided by 3/2. And then x to the -5th, you're going to get x to the -5 plus 1, which is -4, divided by -4 plus c. I would not leave this 3/2 in the denominator here. That feels gross to me. I would probably prefer to rewrite this as 1/4 times x to the 4th plus 2/3 times x to the 3/2 minus 1/4 x to the -4th. Let's see. Notably, or maybe not, actually not notably at all, not at all notably, if you take the derivative of this, you should exactly get back the function you started with. The derivative of 1/4 x to the fourth is 1/4 times 4x cubed, which is x cubed. The derivative of 2/3 x to the 3/2 is 2/3 times 3/2 times x to the 1/2, which is exactly x to the 1/2. The derivative of negative 1/4 times x to the negative fourth is negative 1/4 times negative 4 times x to the negative fifth, which is just x to the negative fifth. No surprises here. So the bigger statement here is that every derivative you knew how to take, you learned how to take in 17A, all those answers, right? All the derivatives, you know the antiderivatives of them. They're just the functions you started with. So let's make a quick little list of functions we know. Yes, question.
Could you give us the anti-power by
Oh yeah. Yes, that was the one I was first one I was going to start off with. So we're going to make a list of derivatives we know and their corresponding antiderivatives. So yes, generally, let's see. I kind of want to make this so I think I'm like terrible. Yeah. So let's say we have do it like this. We'll say f of x and f prime of x, and then over here, f of x and the antiderivative of f of x. So power rule. If your function is x to the n, the derivative is n times x to the n minus 1. The anti-power rule, if your function is x to the n, your antiderivative is x to the n plus 1 divided by n plus 1 plus c. Because one value n isn't allowed to equal. If n was equal to -1, we'd have some problems. -1 plus 1 is 0. We can't divide by 0. This is true as long as n doesn't equal -1. So that actually begs the question, what if n was equal to -1? So if we have x to the -1, which is 1 over x, what function has a derivative that's equal to 1 over x? Right. Now, we won't get into it right now, but the natural log of x actually isn't the most general antiderivative of 1 over x. It's the natural log of the absolute value of x. Let's see. And we'll talk more about that a little bit later. It has to do with the domain of those functions. Over here, if your function was the natural log of x, your derivative would be 1 over x. Another fan favorite, if your function is e to the x, your derivative is e to the x. Your function is e to the x, your antiderivative is e to the x. Let's see. Good times. In fact, there's one other one I wanted to get to before the trig functions here. Oh, I know what it is. So if your function was, let's just make up something. Sure. Let's say it was 3 to the x. What's the derivative of 3 to the x? There is a logarithm in there. It's very similar to e to the x. So the derivative of 3 to the x, or more generally b to the x, is 3 to the x times the natural log of your base. Now here's a fun fact that I'm going to harp on a lot. If you have a function and you take its derivative and you end up multiplying by a constant, that almost always means that when you take the antiderivative, you end up dividing by that constant. So here, the derivative of 3 to the x is 3 to the x times natural log of 3. The antiderivative of 3 to the x is 3 to the x divided by the natural log of 3. Or if you prefer, it might be easier to see, it's 1 over natural log of 3 times 3 to the x. So if you look at this thing here, if you were to take the derivative of this, in fact, let me just write it down here, just to make sure you really believe me. If I was to take the derivative of this constant, times 3 to the x. What happens to constant multiples when we take the derivative? What do I like to say? They hang out is what they stay, right? Constant multiples hang out. Just like, right, the derivative of, 5x to the 7th, that 5 doesn't go away. You get 5 times 7x to the 6th, but we usually skip that step and just say it's 35 times x to the 6th. Same deal here. This constant, that's what that is, right? There's no x's there. That's a constant. That's going to hang out. And we're going to get 1 over natural log of 3 times the derivative of 3 to the x, which is 3 to the x times natural log of 3. Oh, what's going to happen to the natural log of 3's? They're going to cancel. That's why that works, by the way. If the derivative makes you multiply by a constant, the antiderivative makes you divide by that constant to account for the eventual multiplication by the constant if you were to take the derivative at the end of the thing. This idea does not go away. This idea that if you take the derivative and it makes you multiply by a constant, the antiderivative is going to divide by that constant is kind of not the only thing, but one of the main things U substitution is useful for. So I will definitely say this a lot, that, the derivative is going to make us multiply by 4, and the antiderivative is going to make us divide by 4, or something like that. Let's go back to our list and we'll come back around to that idea, because I think that idea is actually super, super important. It's going to save you a lot of time if you're not always having to write it all out. Let's see. We have our powers, we have our log, we have our e to the x, we have our b to the x. You know what it's time for now. What's missing? The trig functions. So let's write them all down. We've got sine, we've got cosine, we've got tangent, we've got cotangent, we've got secant, we've got cosecant. The derivative of sine is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. The derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. A reminder that every co-function, cosine, cotangent, cosecant, has a derivative that starts with a negative. That's how I remember. The co-functions have a negative derivative. So then, since we know that the derivative of each of these are these things, we know that the antiderivative of these things are those things. So the antiderivative of cosine of x is sine of x plus a constant. And instead of saying the antiderivative of negative sine is positive cosine, I'm going to say the antiderivative of positive sine of x is negative cosine of x. Again, you can always multiply really anything by a constant. So like whether it's a summation like we saw at the beginning of class, or derivatives like we saw last quarter, or antiderivatives, constant multiples just kind of stick around. So if I know that the derivative of cosine is negative sine, I also know that the derivative of negative cosine is negative sine, which is positive sine. It's totally valid. Just multiply everything by -1. The antiderivative of secant squared of x is tangent of x. The antiderivative of cosecant squared of x is negative cotangent of x. I should be saying plus c here. The antiderivative of secant of x times tangent of x is secant of x plus c. And the antiderivative of cosecant of x times cotangent of x is negative cosecant of x plus c. I'm at like a little bit more. Make sure people can really differentiate between things here. Terrible math joke, I know. So this is almost an exhaustive list of all the types of functions we currently know how to differentiate and anti-differentiate. Later on, I think I have to check myself. We will probably learn how to find the antiderivative of tangent of x and cotangent of x, maybe secant and cosecant. I don't know if we do those ones or not. There's one other function I can think of that we know the derivative and antiderivative of. We did learn last quarter, I believe, that the derivative of the arctangent of x is 1 over what? Plus. I remember it's a plus because tangent starts with t and a plus looks like a t. So the antiderivative of 1 over 1 plus x squared is the arctangent or the inverse tangent of x plus c. And that's a fairly comprehensive list there. Cool. Let's see. Yeah, we should just get into it. So, a couple things. One thing that I would say is generally pretty true is usually worthwhile. Wow, to spell things nicely. Can you read that? That says worthwhile. It is usually worthwhile. Oh my God, that's terrible. To simplify an expression before really doing anything, before differentiating or anti-differentiating is what I was really getting at though. So for example, if I was trying to say find the antiderivative of f of x equal to 3x squared plus 2x times 4x cubed plus 1. I'm going to say something that is kind of technically not true. It's fine. There really isn't an anti-power rule product rule. Like there, or I should say, there isn't an anti-derivative product rule. Technically, there kind of is, but it's not what you would think of. So there's not like a nice like f prime g plus f g prime kind of thing. It doesn't work that way. So to anti-differentiate this, it really is easiest if we just multiply it out first. 3x squared times 4x cubed is 12x to the fifth. 3x squared times 1 is 3x squared. 2x times 4x cubed is 8x to the fourth. And 2x times 1 is 2x. And now it's much easier to find the antiderivative. The antiderivative is going to be 12x to the sixth over 6 plus 3x cubed over 3 plus 8x to the fifth over 5 plus 2x squared over 2. I know I could be skipping some steps here, but I'm not. And you should not leave this unsimplified. It would be a crime. This is 2x to the sixth plus x cubed plus 8/5 x to the fifth plus x squared plus c. I will point out, this is a matter of choice here. You can write this as 8/5 x to the fifth or 8x to the fifth over 5. Either way is totally perfectly acceptable. Just make sure that x to the fifth doesn't somehow end up in the denominator. It's in the numerator or off to the side, but not in the denominator. In a similar way, I could ask you to do something like find the antiderivative of x squared plus 3x plus 4 divided by, the square root of x. Pain in the butt. So just like the previous one, there isn't an anti-quotient rule either. So your job here before you start trying to find the antiderivative is to simplify this expression, to rewrite it as each term x squared divided by x to the 1/2, or 3x divided by x to the 1/2 plus 4 divided by x to the 1/2. And then rewrite each of those things as just x to a single power. We can't deal with stuff in the denominator really. We have to write it as x in the numerator or just kind of on its own to some simplified power. This is going to be the antiderivative of x to the 3/2 plus 3x to the 1/2 plus 4x to the -1/2. And now you should go ahead and finish doing the antiderivative here using the anti-power rule again. Oh, we're almost out of time. Time flies when technology's not working. Or even when it is. So since I do want to get to this last thing here, well, next thing, let's finish this off. We're just adding 1 divided by the new power. So 3 halves plus 1 is 3 halves plus 2 halves, which is 5 halves. So we're going to get x to the 5 halves. Instead of dividing by 5 halves, we're going to multiply by the reciprocal. Same deal here. We're going to get 3 times, we're going to add 1 to that power. We're going to get x to the 3 halves multiplied by 2/3. Over here, we're going to get 4 times, I'm leaving some space here, x to the positive 1/2 divided by 1/2 is the same as multiplying by 2. Yes, I should simplify that, but I'm not going to because I really want to make sure you see one more example. Don't leave just yet. This next example is important. Okay. Okay. So just real quick, I just want to show you this one thing. So where'd you go? I lost my spot. There we are. So let's say we have this function. We want to find the antiderivative for f of x equal to, what have I got here? E to the 3x plus sine of 2x plus secant squared of 6x. So here's where we're going to use that same idea about if the derivative makes you multiply by a constant, the antiderivative is going to make you divide by that constant. What's the derivative of e to the 3x? Right, e to the 3x times 3. E to the 3x times 3. So our antiderivative, well, for e to the something, it's still e to the something, but our antiderivative is going to be e to the 3x divided by 3, or times 1/3. Because look, if you took the derivative of that, the 1/3 would hang out, and the derivative of e to the 3x is e to the 3x times 3. The 1/3 and the 3 multiply to 1, and you're back there where you should be. Same deal here. If you took the derivative of sine of 2x, I don't really care what the function would be, you would get cosine of 2x, and then you would multiply by 2. So the antiderivative, which is going to be negative cosine of whatever you have, is going to be negative cosine of 2x divided by 2. We'll multiply by 1/2. Same deal, right? If you took the derivative here, the negative 1/2 hangs out. The derivative of cosine of some stuff is negative sine of that stuff times the derivative of the stuff. So the derivative here would be exactly negative 1/2 times negative sine of 2x times 2. Oh, look, that's exactly sine of 2x. Lastly, again, I don't actually know off the top of my head the derivative secant squared of whatever, but I just care that I know if I took the derivative of this, I'd end up multiplying by 6 when I use the chain rule at the end of the day. So I know that my antiderivative should divide by 6. So it should be 1/6 tangent of 6x. Because I know that the derivative of tangent of 6x is secant squared of 6x times 6. And then the 1/6 and the 6 will end up canceling out. So that's really what I wanted to make sure you saw, is that when you're trying to anti-differentiate things and the argument of your function is a little bit more complicated than just x, it's a multiple of x, you almost always end up dividing by that multiple of x at the end of the day. Also notice that the argument itself, the 3x, the 2x, and the 6x doesn't change, right? The stuff that's stuck inside the function is stuck and usually unchangeable. Someone described it once upon a time to me as the trig functions acting like bodyguards, right? Like they're protecting stuff inside and you can't mess with it, you're stuck. All right, that's close enough to 11:50. I'll see you all on Thursday. Hopefully the technology will go a little bit easier. And if there's any questions about the syllabus between now and then, feel free to email me, or you can ask them at the beginning of class on Thursday. We can cover it. But again, it's really pretty straightforward.